Hello everyone, let's get started. In this session, I will talk about groundwater model calibration. Again, the main reference for this session is Applied Groundwater Modeling book of Mary Anderson and Wisner, and graphs, figures, and plots. Many of them are coming from this fantastic book. Okay, as you remember, once we were talking about how we can design a proper conceptual model, we talked about the complexity of the natural system, and we said that technically to develop a proper and designable groundwater conceptual model, we have to do some simplifications. And we talked about this, that actually we said that this simplification does not necessarily mean bad. So based on the knowledge and based on the tools that we have, we better do some sort of simplification, but everything depends on the experience and knowledge and data that we have. So we already talked about those, but we know that our conceptual model is simplified. And after that, once we wanted to map the conceptual model into the numerical model, we had to again add a little bit of uncertainty due to space discretization and time discretization. And also we said that the parameter assignment is usually we don't have enough or too many hydraulic properties, for example, hydraulic conductivity, storage coefficients, and recharge information, also pumping information. So usually we have some sort of averaged information, both spatially and temporally. Okay, so for example, about the hydraulic conductivity, we said that we usually have a few field measurements, and we have to assign this or extend these numbers within the entire space. And again, the boundary conditions and the packages that we talked about. So these are the source of simplification of our groundwater model. So based on these simplification, we go and design a numerical model. Okay. And after that, we want this numerical model to go and solve for h or phi at x, y, z, and t. All right. So, and we have a tool of ModFlow, which can go and solve those partial differential equations and find the head at each x, y, z, and t. But how we can go and judge how well our simulation is. Okay, so technically to estimate or to evaluate the results of our groundwater model, we have to use some field informations or field observations. So technically you go to the field, for example, if this is your field, so you model this system, but you have some monitoring wells here, here, and here, and you have some observation data here. And you technically want to match to see how your model simulated the head here and how you measured it in the field. And based on that, you judge how well your model is. Okay, if you remember, we divided the groundwater models into two main groups of forward modeling, in which you input hydraulic parameters or sink and source terms, and technically you go and solve for head or flux. So this is a forward form of groundwater model, but in practice we have more accurate and reliable field measured values of heads and fluxes comparing with the hydraulic parameter values. It means that we here in this part, when we input the hydraulic parameters or properties into the system, there is a huge or considerable notable amount of inaccuracy in our parameters. So it doesn't matter during the measuring the hydraulic conductivity at that specific location, or due to the extrapolation or interpolation processes. So, but we can say that the groundwater head, which were measured or observed at the field, are usually much more reliable compared to the hydraulic properties that we have here. So because these are usually these are point information, so you spend enough time and energy here, and technically you go, and based on the tools that we have, you can simply go and you put the transducers, or there are other multiple ways, but you can go and have or make a good and reliable database of head and flux in the field. Okay, so because of that, people proposed another form of groundwater modeling, which we called inverse or backward modeling. So in the backward modeling, essentially our input value, so we have the information at the monitoring wells, and we go and change the Ks or sink and source of values to match the observation with the simulated results. So technically now these are the unknowns. Okay. So this process, the process in the inverse modeling is called calibration, and the objective of calibration is to identify a set of parameters that produces a satisfactory match to the field observation. Okay, to do that, the procedure is almost the same. So these are the main steps that you take to inversely model your system. First, you need to select some calibration targets, so which are technically usually our, for example, it is the groundwater head fluctuation information, or that might be the amount of flux or flow information into the river, lake, and information like this. So you have to go and find some good calibration targets. Then you need to think about the reasonable range of the hydraulic properties, and also forcing hydrological forces like recharge, ET, and so on, and you need to define a reasonable range for your parameters. Then you go and run a set of forward models. You run forward models, you go and find phi, and then you compare your simulation with the observation, and based on that you correct or you change your input values, and you come back and again and actually repeat this loop until you get a good or close simulated and observed values. Okay, so this is the general procedure. This flowchart shows a similar procedure, a systematic way to go and find or calibrate the model, but we can categorize the calibration methods into two groups of that would be better to say manual trial and error, and second is the systematic optimization methods or systematic trial and error. So I think that would be a better labels for these procedures. So the manual trial and error and systematic trial and error, or numerical trial and error, so that we are going to talk about in the next slides. Okay, in this session, I don't want to spend time to go and think or talk specifically about the systematic mathematics of calibration, but what I want you to learn here is that I want you to learn why calibration is important and how we can judge and decide that we have done a good job in calibration. So these are my main objective and goals. So we usually have very good, in next slide you will see that, and also you're going to practice this calibration as a homework. You'll see that there are some softwares which help us to calibrate our groundwater models, and we as a groundwater modeler, not necessarily we need to know the very advanced and complex mathematics behind the calibration methodology, but and the GUIs that we have, they have done a great job, and they've created a very easy and practical interface that we can go and apply those calibration methods. So the mathematics or the calibration method is not my focus, as I said, but I want you to know the philosophy behind the groundwater calibration. So here, technically, as you can guess, if you created a model and if your model cannot sufficiently simulate or create the phi or head information or flux information at different locations and at different times based on or compared with the measured field measured data, then you can say that this model is unreliable or inaccurate. Okay, so that is very intuitive. However, if the model produce even however, if you have a model and if you see that your model, for example, suppose that this is the fluctuation information, and your model have created very good results like this, it does not necessarily mean that it is right, or it does not necessarily mean that it is a reliable and accurate model. Okay? So technically, if the model produces good fit, it does not necessarily mean that the match is acceptable. So we call this hard knowledge. That actually, this is a very important thing that I want to spend time and discuss this. The match is acceptable only if the estimated parameters and assumptions are reasonable. What does it mean? And we call this soft knowledge. What does it mean? It means that, for example, you go and, for example, suppose that this is your conceptual model and you have one monitoring well here, and you create a very good match like this, but you see that, for example, the K value here, for example, suppose that this is a sandy aquifer and you expect a relatively high hydraulic conductivity based on the geological information that you have. But your model has created a very good fit, but the K value is so low and they are in the clay range. Okay, so this is one example. Okay, so this way, this is a soft knowledge. The geological information knowledge that you had was a soft knowledge, but you need to technically, to do a calibration, you have to check both the hard knowledge and soft knowledge. So your model should create a reasonable and accurate enough, the head and flux information, and also the calibrated values should also make sense. Okay, so this is very important, that actually usually people, I've seen that actually so many cases which they have created a very good fit, but they didn't think, or they didn't discuss the soft knowledge part, or the additional information that we have, that actually we want our model match with those information as well. Okay, that would be hydraulic property, that would be, for example, the flux information under a piece of or section of river or lake, and or pumping rate, recharge rate, such information. Okay, so essentially you need to check both hard and soft knowledge, but checking this part is not usually very easy. So you have to have a very good expert knowledge, you have to have a very good geological and hydrological information from the site, which you can go and find from the reports, papers, and also you can talk with people and researchers. Okay, so and also you have to have a basic hydrological theory, or you need to know the basics of the hydraulics. Okay, so for example, if you are for example, if you have an information of flux or velocity directions and so on, so you need to actually check your model to see that actually it is hydraulically sound. As I said, the model is calibrated if it passes both hard and soft knowledge assessments. And typically, most effort and reporting focuses on the model's ability to fit observation, because you can go and quantitative or visually or quantitatively show the fit. So if you go and see the papers, they usually they have done a very good job on fitting the data, but they have a very weak and incomplete discussion on the evaluation of models. Adherence to soft knowledge is something which is lacked usually in those reports. And the problem is that usually it is difficult to go and quantitatively show or represent the soft knowledge matches, but you know, I mean, there's no way you need to go and convey the matches in the soft knowledge part just by verbally describing the system and describing the soft knowledge information, and say that actually our model matches and consistent with these information. So herein I want you to learn or think again about the basics or philosophy of groundwater modeling and groundwater calibration. As you know, groundwater models simulate a part of complex natural world, which is impossible to characterize completely. So it is almost impossible. You go and measure the hydraulic conductivity everywhere. It doesn't matter. Even in very small laboratory scale problems, we have difficulty to go and find a very proper and accurate, especially in temporally distributed information. In the big scale and field scale problems, definitely this problem is much more worse. So we can say that the field scale groundwater model is always a simplification of the true hydrologic system. So the simplification is the word that I want you to think, think again, and you need to learn that all groundwater models that we have, it doesn't not necessarily groundwater models, all models which simulates the processes in the natural world, they all have a level of simplification. So I put the word, I tried to divide the field scale groundwater model from the laboratory small scale laboratory scales, because in the laboratory scales, since it is a smaller problem, you as a modeler have a control, and we ourselves, we go and set up our laboratory model. So we go and create a specific K values, S values, and so on, and we have a better control on the system. That's why the level of simplification in groundwater the laboratory scale and small scale models is maybe less, but still there is some sort of simplification during those types of studies. So in the field situation, we usually, I may say that always have more unknown parameter values than known field measurements. Okay, so if you think about this, the measurements that we have mathematically, they are actually our constraints. And you will see later actually what I mean by constraints. But usually we have a very few. For example, we have only 5 monitoring wells within, for example, a 5 kilometer, 1 kilometer problem, or we may have just very few K values here and here and here, but technically the K values in other points are unknown, right? So this is technically, we would like to go and create and find the K values, for example, everywhere, and compare them with the measured K2 values. And based on this, actually we proceed calibration process. Okay, so we usually have very limited and few known and observed values, which cause a problem. And also the inverse and because of this, the inverse problems are technically undetermined by observation, and we call them mathematically ill-posed. So the mathematically ill-posed problem means that since you have very limited constraints or known values, technically there is no unique solution for your problem. It means that there is a group of solutions which can go and create a very good match. For example, if this is the observation and simulated at this point. Okay, so there are multiple scenarios of the distributed K values or S values here, which can go and create a reasonable and close simulation. That's why our groundwater models are inherently ill-posed, or they suffer from non-uniqueness. Okay, so but there are some ways that actually we can address this problem. So how we can address the non-uniqueness issue? First, we as a groundwater model, we need to go and identify a family of possible and reasonable solutions for our model, which herein I call them hypotheses. So we have a group of hypotheses, like I don't know, 5 different models and calibrated results, which creates a reasonable match with our observation and also with soft knowledge. Okay, so remember, we have to check both hard knowledge and soft knowledge, both. So we have 5 hypotheses which passes these tests. Then, so groundwater modeler should technically express the groundwater processes, which are the groundwater flow information, the velocity, direction, by multiple working hypotheses. Okay, so groundwater modeling can be said that essentially the main objective of groundwater modeling is to go and test hypotheses rather than a matter of finding the optimal model. So it is much more reasonable and it is much more defensible and accurate if we go and find a group of hypotheses, which are usually, they are not too off actually from each other, but some of them may have, for example, have better results once we test the soft knowledge and hard knowledge information. But it is good to represent the system using a group of hypotheses, or we can go and discard the other models and hypotheses which are out of this group, which is important. So there's a very nice discussion on the Bevan paper published in 2009. If you're interested, you can go and read the philosophy of the groundwater modeling. But in practice, once you sign the contract, your client or the decision makers that you are working with, he or she wants you to come up with one solution. So technically, they don't understand or they don't know the complexity and the reason why we say that this level of knowledge and technology and information that we have, it does not let us to go and directly go and find the best options. Okay, so they usually don't understand the system, and I think this is part of our responsibilities as groundwater models to go and change this viewpoint to groundwater models. But anyway, so you are usually asked, or you are supposed to submit one solution to your problem. And what is that? That solution is actually the best solution which you can go and pick and you can find from the group of solutions that you have. Okay, but how you can do that, we're going to talk about this in next slides. Doherty and Hunt has explained this situation perfectly from my viewpoint. They say that the selection of model that is considered the best representation of the natural system is always subjective. So it is always subjective, even if unlimited resources and time were available. So what they want to say that finding the best representation of, or the best solution depends to so many different things, like the objectives of the modeling, modeler itself, or in some points maybe the client or decision makers that you are working on. It may depend on the amount of time that you have for modeling, or amount of funds that you have to do this. But what you need to know and learn is that always finding the best calibrated model is subjective, and that's why the experience and knowledge or gained knowledge is something which is very important in groundwater modeling. It is like it is like an art. So you need to experience, you need to learn the tricks to become a good groundwater modelers. But it is very, very important to pay attention to this fact that although you may find the best model from the family of reasonable solutions that you have determined, but you need to, and this process is subjective. Okay, so you subjectively go, and based on these information and based on your experiences, you go and find, for example, 5 hypotheses or 5 solutions, okay, which you think that they all pass, they pass both soft and hard knowledge, okay? But you need to pay attention that the solutions, the hypotheses out of this family are objectively discarded. Okay, so technically you have objectively checked the soft knowledge or hard knowledge, and you said that these hypotheses they cannot be true. So there are so many other hypotheses that you can go, and this process is an objective process. Okay, so which is very important, and that is the main goal of groundwater modeling in so many cases. There are multiple ways to go and represent the goodness of your model, or to go and decide or pick the best solution out of the family. One way is that you can go and visually plot the observed and simulated head and flux data. So there are multiple ways. In this slide and next slides, I've shown you some examples. For example, in this map, you see that actually there are different contours. One's is red, the one is the computed, and the green is the observed. So based on this visualization, you can go and find the best solution. For example, if this is the main area of your interest, you can focus on, and based on that, find the best solution, for example. Or you can go and plot the observation and simulated results in a specific location and actually plot them, and based on this you can go and actually compare the goodness of your simulated results and calibrated results. The other way is that you can go and plot the residual errors. So the residual errors is, by definition, is the difference between the measured and observed. So this is another way that actually you can go and represent your results, or you can use quantitative statistics to measure the goodness of fit, for example, mean square errors and different forms of errors that actually you can go and use them and statistically and quantitatively show the goodness of your simulation. In this picture, you see how you can represent the residual errors and show the high expected and low expected values, and actually compare your results or discuss the goodness of your model using this type of information. Or you can go and plot the target values versus the simulated values and create a plots like this and discuss the goodness of your model. As you can guess, there are three types of data that we can use as calibration targets. One is the head information, which technically comes from the monitoring wells, the flux information, which comes usually from different and independent studies and measurements, and also the hydraulic properties are, for example, you can set a range of K values or S values for a specific location, and you can use them as your calibration targets. But specifically speaking for heads and flux, and maybe in some cases that might be the hydraulic, for example, yeah, I mean, actually, if you think about the recharge and ET terms, so you know that these values, like groundwater table, it fluctuates and it changes with time. It's seasonally, and in some case maybe daily. So we usually, it is very difficult to go and use all of these information for the calibration. So technically we can go and again use an average data or average information to go and better calibrate our models. But it is very important to know that you have to have a good and reasonable calibration and to create a reasonable groundwater model, you need to rank your target values. So for example, that would happen, you need to think about the location of your target values, you need to think about the objectives of your model, and also you need to think about the accuracy of the measured values. You know that, I mean, for example, we said that, for example, if you want to go and find K values, so there are multiple ways. For example, you can use a slug test, or you can use a pump test. Okay, each of these has their own limitations and approximations. Okay, so they are not accurate, and also the human error can play a role here, and it can create actually an error in our estimation. So these are the things that actually we need to think about. But for example, if there is a factory here that we want to know how the groundwater is moving beneath this, or how the contaminants which would move by the groundwater models. So technically we can say that if we have a monitoring wells here and here and here, maybe we can say that I don't know, this is just a suggestion. I would say that, for example, I can rank these as the most important, and this is the second important, and the upstream is the least important points. Okay, so then if I have a family of solutions, I will go and focus on these targets. Okay, and that would be, again, I need to think about, that would be, for example, this is just a location example. Okay, so you need to think about, so again, based on the objectives, I said that the contaminant transport was an objective. That's why actually I said that the upstream may not be very important, but these are the things that you need to go and think about. So technically, you need to go and rank your target values and constraints, and if you see that actually it is better to ignore or discard some calibration points, it is you can go ahead and actually do that. Okay, we said that there are two methods to do the calibration. First is the manual trial and error. The second one is the automate trial and error. Okay, so the processes are kind of the same, but the difference is that herein you have to do the iterations manually, but here there is a systematic way and software which uses very advanced mathematical and statistical calculations and considerations, and it goes and creates or solve our calibration models. But there are a few things that I want you to pay attention to and think about. It is very important that although you usually will be required to go and use an automate trial and error method, but before starting this, you should go and manually try to do the calibration and play with your model, because by doing so you will see that actually you will gain a lot of useful insight about the site, which can help you in soft knowledge assessments. Okay, so technically you need to go and play with the parameters and do the calibration manually and see actually how the results change and how your system works. The manual trial and error can quickly demonstrate that the conceptual model is ill-situated. So if you do the manual, if you do the trial and error manually, and if there is a significant problem with your conceptual model, it will go and show you. But if you miss this process, and if you directly go here, it is very difficult, because these are very time consuming and there are so many details that you need to be taken care of, which may distract you, or it may take your time, and it might be too late to realize that you need to go and revise your conceptual models. But the trial and error method is easier, it is faster, and it is much under control of the modeler. That's why it creates very good information insights about the model. So as you can guess, it is intensive, it is frustrating, and it is very subjective. So you need to be very patient. You need to know that before starting this, you need to know that it's a very frustrating process, and you need to actually do a trial and error a lot of times. But you need to know that this method cannot guarantee that the modeler has found the quantifiable best fit for your solution. It means that there might be many untested values that you didn't have time, or for some reasons you couldn't go and test and try them. So this is the big drawback or the big limitation of the calibration. But you don't have this problem, or you have a very less impact here in the systematic trial and error, because it goes and iterates your calculations a lot of times, and it itself goes and tries to go and find the best hypothesis and best scenarios and focus itself to that area. Now, in groundwater model world, we usually extensively use the calibration software known as PEST, which stands for Parameter Estimation Software. It is developed by John Doherty. John Doherty has done a great job here. He spent a life actually, and he created, I think it might be, if I'm not wrong, maybe it is a 30 years effort of John Doherty to create a very advanced and sophisticated model known as PEST, which is freely available. So you can go and it's an open source software. Okay, so you can go and actually, if you want, you can go and use this, but it is not easy to use that. So you need to get trained usually or study to be able to use the software. But there are a lot of GUIs and interfaces like GMS, which are actually, they have the PEST feature that you can go and use the interfaces and do the calibration. So you don't need to learn the advanced mathematical and statistical methods or the very detailed knowledge underlying this theory, but you need to go and learn how you can apply this PEST method for PEST software or PEST solution to your developed groundwater model. So you're going to solve a few examples, calibration examples, and I want you to go and play with and gain some experiences on the calibration. This is, as we discussed, the calibration process depends on the experience and the knowledge, and it is subjective. So you need to spend time. If you want to be a good groundwater model, you have to be a good calibrator, or you have to learn how to calibrate your models. But it is very important, and I've seen this problem a lot, that there are some cases in which they have spent too much time and effort on designing the model, and they've just left 1 month. For example, they spent 11 months on designing, conceptualizing, and designing the groundwater model and solving it, and they have just left 1 month to do the calibration. So this is the so you need to be careful with that you shouldn't start your calibration model too late. So it takes time. There are a lot of steps that you need to take, and this is the way that actually you can show that your model works right. Okay, so this is the only way to go and judge that the model that you have created is right. Okay, I will finish this course here, but before doing that, I want to talk about one thing, which is that actually in this course we specifically focused on groundwater flow. So we had the governing equations which went and if we solve that equation, it will give us h or phi information at x, y, z, and t. And based on that, we can post-process this information and we can find the gradient or the directions or flux and so many other information after post-processing this information. But groundwater modeling does not stop here. We usually want to find how the head is distributed within the system. We want to find the groundwater head contours because we want to find the groundwater velocity and direction at each location. So this is something that actually we want to know. But there's another group of problems which we call them contaminant transport. So the contaminant transport has a similar governing equation but its own governing equations, which technically gets the flux and flow information from the groundwater flow model and use those information, technically the velocity information, and they go and solve how the contaminant changes at each x, y, z, and t. So we didn't talk about the contaminant transport models in other class of mine. We specifically talk about the governing equations of the contaminant transport, and we learn how we use the information here and apply it here to see how the contaminants, how the plumes will move within the system. But this is a very similar process. So the process of the contaminant transport and the groundwater flow is very similar. It has its own governing equations. There are some methods and softwares and packages like MT3D or RT3D that actually we discussed these in other class. But they have their own packages, and you need to do the find this, and eventually you need to go and find the calibration. Actually do the calibration. So the process is pretty much the same, but with different groundwater, but with different governing equations technically. So I believe that actually by the knowledge that you've gained by taking this class, you can go and learn and practice the contaminant transport modeling as well. I hope you've enjoyed this course and you've learned useful techniques and skills to become a good groundwater modeler in the future and probably build your career on. If you have any questions, you can send me an email as you did before, or you can stop by my office. We can work on your questions, and I hope that you've learned the main objectives or the main goal of mine was to teach you in a plain and simple language what is the philosophy of groundwater modeling and how you can create an accurate and reliable groundwater models. And I hope that actually you've learned new things, but there are very good sources around that you can go and learn. I believe that you right now have the basics of that you need to know from groundwater modeling, and you can go and learn all other stuffs that you think in the future that you will need to learn more about. So I will stop here, and I wish you the best. Good luck.